Okay, thanks Prateek and Nisheeth for organizing this very nice workshop, and thanks to all of you for sticking around. I'm going to be talking about the problem of robust regression. A few problems to motivate the problems that we'll be looking at. Let's consider a recommendation system problem where we have a user who is being offered items, maybe on some website, as Swati was mentioning during her talk, and this user offers ratings to each of these items, so indicating how much the user likes these items. So the user really loves apples and grapes apparently, but not so much lime and strawberries. The goal in recommendation system is to be able to model the like behavior of the user. What does the user like? What does the user not like? In an effort to be able to recommend future items. And you can do this by, let's say, casting this as a simple linear model. So the preferences, the ratings are, let's say, a linear function of some encoding of each of the items. And so there is this model vector which encodes all the user preferences. So this is very well studied, and the whole area of linear bandits and linear contextual bandits has evolved to study this model and execute this model in online settings very well. However, what adds a twist to this problem is if we have this adversary which comes and sort of morphs some of these ratings. So this may be click fraud happening. So you clicked, but the click didn't get registered. Maybe there's malware on your computer, or else the other way around. You did not click, but a click got sent. Irrespective of whatever happened, we don't have, at least for these few items, the actual ratings the user had for these items. So the question is, so what we get is a morphed, a distorted view of the rating. So the question is, can we still recover the user model? And so one response to this question would be to, let's say, okay, fine, this is just noise. Why don't we just go ahead, like force through the usual methods, and this noise will probably be handled by the algorithms themselves. But there's a catch here. These corruptions are not benign. They are deliberate. They may be malicious. It's inappropriate to model them as Gaussian noise. And we'll see that it's not just in theory. It's in practice also. It's inappropriate to model them. X is a vectorial representation of this item. So the item code, the past history of purchases, some way of representing the item as a vector. I represent the user as a vector. The inner product between these two vectors gives me an idea of how much does the user like this item. I get to see Y. Y star is what I would have seen had the user been allowed to give all the ratings. I know X, I don't know W star. So I know my items very well. What I don't know is the mind of the user. In this cooked up example, I'm attributing this to click fraud. So clicks, you can think of them as CTR estimates, but if there's click fraud happening, you won't get CTR estimates. So if there's an ad campaign going on and someone wants to derail their ad campaign, they will suppress clicks for certain items, maybe of the competitor brand, or boost up clicks or other inject clicks for their brand, and which is exactly what is happening here. But this is just a very cooked up example, although we will look at some experimental results on a similar setting. Another example to motivate what we'll be looking at is, so by the way, this problem gets a bit more complicated because this is an online problem, because these items and these ratings we are not getting in one go, we get them one at a time. But we'll not be worried about this online aspect of the problem. The second problem I want to put forward is a nice biometric identification problem. We have a database of users. We have several images that the users have registered on the database, and we now have a new image or a new face being presented to the database, and you want to find out if it's one of the persons that has been registered or not. One way to do this would be to try and see if we can express this new image as a combination of the existing images. Again, same model, but in this case, these weights that we get as a side effect of representing the new image as a function of the old images can reveal the identity of the person, because in this case, as we say, 0.4 and 0.3, these are the same person. These are images of the same person, whereas images of other persons get very, very small weights. Again, if our friend here appears and does something different now. So this is not a very good example, but think of the person as wearing goggles or having sported a beard. So what happens? In this case, what you get is an image, but the image plus some mask, which is hiding some portion of the face. Maybe the eyes, maybe the nose, part of the face. Again, what we get to see is not the clean signal, but the clean signal plus some corruptions. The question is, can we still perform the same operations? And again, here it is not salt and pepper noise that's being added. The noise is very, very structured, very, very deliberate. So it's not okay to say, okay, this is Gaussian noise. Least squares will handle it. It doesn't work that way. Again, I'll show you that does not work. Like least squares or something like that treats this as Gaussian noise fails miserably. As you may have figured out by now, what I'm alluding to is the general area of robust learning and estimation. This has been a classical area in the field of statistics dating back to the 60s, classical texts by Hooper and Tukey, but it has experienced a newfound interest, and several works in the past 5 to 10 years have looked at the problem from various angles: robust classification, robust regression, robust PCA. This is some work that I'll be looking at, Praneeth's work, robust matrix completion, very recent work, robust optimization, and robust estimation. Pravesh was looking at some of these issues in his talk. An extremely exciting area from both a theoretical and application perspective. So let's look at some applications, like actual applications, not the toy ones we looked at. So the first application of robust learning and estimation techniques is when the data actually gets corrupted. Well, let's say if you have recommendation systems and we have click fraud happening. But that's not the only area in which the only case in which these have been applied. So robust learning and estimation techniques have also been applied when the data is not corrupted, but they are used to reformulate learning problems. So for instance, one very favorite example is actually an application that Praneeth and Prateek worked on casting foreground background extraction as a robust PCA, robust principal component analysis problem. And this is again, these videos are taken from their work. So you want to separate this video as a background plus the foreground. And this is the actual output of their algorithm. This is robust PCA working. There's no corruption here, so to say. But the problem was cast as a robust PCA problem, and you can see the quality of extraction. I mean, this is virtually an image, looks like a still image, although this is a video. It's almost perfect extraction. Similarly, questions such as image in painting can also be cast as robust regression problems. Basically what the biometric example I said. So you have, let's say, pictures where crucial parts of the faces have been taken out. What least squares would give you something like this if you were to solve the least squares problem. But I will show you a technique which can do a much better job. Something like this. It's still not perfect. You're still not able to recover the face exactly, but I hope it's clear that the reconstruction is much, much better. Again, same least squares give you this, but it'll get better. Yeah, so it does get better. Much better if I say so myself. I'll come to this. I'll come to this. So I don't have much time. Anyway, I think the clock started in 42 minutes. I mean, I don't know why were 3 minutes taken away. But I don't want to start on something very, very ambitious. So let's look at a very, very toy version of this problem. I'll just look at linear least squares regression for now. I have data points. Each data point is a pair of a covariate vector in R to the power D and a response vector, which is a real valued number. Some of the points are quote unquote clean, which means that for some unknown model, the response is exactly modeled by the model. The response is exactly modeled by this inner product. However, some of the points are corrupted by our friend here. And yeah, as Ramprasad said, we have weird friends. My friend is colored red. There is some additive corruption being injected into the response, and we get to see why. You can say, yeah, there's a BI star here as well, but 0. So I'll keep denoting S star to be the set of n minus k points that are uncorrupted. So k points get corrupted, n minus k remain uncorrupted, and only in the response. Again, this is not the only thing that can happen, but for now, the toy problem I'm going to stick to. The question is, when and how can we recover the model from this data? You'll see an extremely simple intuitive algorithm for this problem. And I don't think I'll be able to go over the proof, so I don't need to apologize. So, but some notation is required still. So I'll just combine all the responses into a vector, all the corruptions into a vector, and I'll take all the covariates and look at the data matrix instead. So I can represent the state of affairs in this one nice formula. I'll assume all the covariates are unit norm or bounded inside the unit norm ball for sake of simplicity. And I'll assume that only k of the points are corrupted. Where k is, I'll make k as much as possible, but for its worth, only k of the points are corrupted. So which means that this vector b star is k sparse. And for any subset of points, so say for any subset S of the set of n points I have, I will let y subscript S, b subscript S denote the appropriate subvectors, and x subscript S will denote the appropriate submatrix. Also, I'll need the covariance matrix because I'll be doing least squares, so I will let for any subset S, CS denote the covariance matrix of that appropriate subset of data points. Yeah, we'll come to that. So let's look at some solution strategies. Obviously, what I want to do is recover W star, but it would be nice, and it doesn't harm me if I discover the clean set along with it. So what I can do is cast that problem as a optimization problem. I want to find the best possible set in terms of the best possible reconstruction error. So I want to find the set of points on which there exists a model which gives me the least possible reconstruction error. So this is the standard residual based least squares objective that we are all used to. So this just, we can write this as in this form as well. So I want to find the best model and the best subset. Best subset, well, I'm hoping that the best subset will be the clean set. I'll assume K to be known. I'll assume K to be known, but yeah, if you don't know, for the purpose of this talk, I'll assume that K is known. If K is not known, you can cross-validate for K. This is a binary search that is not that expensive. It would be to, instead of discovering the clean set, I can discover this corruption vector. If I find out the corruptions and where they were and what they were, I can actually use it to clean up the responses, and I can instead cast the problem in this way. So I want to find a corruption vector such that when I rectify the responses using that corruption vector, I get exact fit or very, very good fit. In fact, this is the starting point for one approach to this problem. Okay, by the way, both these problems, versions of these problems are NP-hard, so because of the combinatorial nature of these problems. So one of the most immediate things one can do is relax these problems. In fact, this problem is just begging to be relaxed. Instead, At the L0 norm, you can have the L1 norm, or you can just do a regularized version of the problem. And this approach is very, very popular and very well studied in many areas, including image processing. Validation, cross-validation. Again, there's even this lambda. I mean, how do you, there's again some lambda which can depend on K, or the theoretical results do require lambda to depend on these quantities. But again, in practice, one cross-validates. Try out lots of values of lambda, find out which gives you the best reconstruction error. I'm sorry? Exactly. R, you don't know, lambda, you don't know. I mean, both of these you have to tune. There is a theoretical relation between R and lambda and actually W star, but you don't know W star. So you try out different values. See, at the end of the day, you want a very good reconstruction. If you are able to get that reconstruction, you are going to trust that value of lambda which gave you that good reconstruction. Oh, this is the L2 squared, the residual error. If the L2 norm, the squared L2 norm, the residual is small, as given by a certain lambda, then you. No. What do you mean by remove everything? You mean this? Oh. Yeah. You're saying, you might say K is N, so remove every point, you have an empty set. No. No, of course, again. No, of course, when you are, so the question is, are you asking this question in theory or in practice? Because I'll be answering this question in theory, but if you're asking this in practice, then in practice, there's a reasonable lower bound on K as well that yeah. I just showed you very, very practical results, and I'm going to prove a theorem as well, so. Yes, so that's what we do. We try out various values of K, and we find the one that, so for every value of K, you will get some W hat. Let's call that W hat K. Every W hat K, and so in all these solutions, you'll also get some SK, which is the set of points that value of K thought was clean. You find out for every value of K what residual error does WK give on SK, choose the one which gives you the least value. And don't let K go beyond, let's say, N by 2. So you can't remove all points. You're not allowed to do that. No, I think K is the number of corruptions. So I think what they meant was set K to N. So remove all points. Then you don't have a vacuous system. No. S is empty. If K is equal to N, then S is empty. So, I mean, that has there's a different thing preventing that from happening. We won't allow K to grow beyond N by 2. Again, let's take this offline because right now I'm way off course. I won't be able to cover even half the things I wanted to look at. So anyway, I don't think that's too big an issue. I think let me give some of the ingredients, and I guess then we can take some of the questions. So I don't want to take the relaxation viewpoint. Why? Because relaxation methods can be very, very slow in practice, and by that I don't mean polynomial time. Relaxation methods are polynomial time, yes, but when I say slow, I mean slow in wall clock time. So we'll see one method that does very well, much better in practice, which by that I mean this. So this red dotted line is the best L1 solver, the dual augmented Lagrangian method solver. And this is the method that I will show you. So all these three are variants of the method. The blue line is a method that I'll sketch towards the end of the talk. And this, as you can see, this method converges even before the convex relaxation method has begun doing anything, because it does some pre-processing. So before the convex relaxation technique has done its pre-processing, the method I'll show you has converged. So it's ridiculously fast. And that's one of the reasons I have no moral issues saying cross-validate. You can run this algorithm several times, and even then your runtime won't. And this algorithm has issues with cross-validation. It can't cross-validate a lot because it takes a long time to run even one execution of that. So how do we do better? So let's reconsider this formulation. Not the correction-based formulation. I want to look at the formulation where we want to discover the clean set of points and the model in tandem. So clearly there are two variables of interest here, the model and the clean set of points. However, what's also interesting is the following fact about this problem. Recovering either one gives me the other. If I know the clean set of points, I just have a standard least squares problem at my hand. Well, in this case, a set of linear equations. If the set of linear equations is well conditioned, determined, at least over-determined, then I can solve the set of linear equations to get the model. On the other hand, if I know the model, then I can just find out which all points have zero error, zero residual error, and it'll spit out S star. It seems that at least at the optimum, there's a bistability. You get me one, I get the other almost for free. So the question we want to ask is are these statements robust? If I don't know S star, but I only have a very good estimate of S star, can I use it to get a good estimate of W star? More importantly, can I get use this good estimate of W star to get an even better estimate of S star? If I can have this thing going, then I am in business, because there'll be a positive feedback loop going on. A reasonably good estimate of S will give me a good estimate of W star, but it'll give me a better estimate of S star, and then these increments will keep adding up, and hopefully I will reach the optimum. Hopefully. So this is the algorithm. Basically 2 lines of code, and even if you code this up in MATLAB, it's actually just 2 lines of code. You start off, you set your active set, let's say. Again, I'm assuming for now that I know K. I know what was the number of points that were corrupted. Let's say just take the first n minus, I say that the last K points were corrupted. I don't know any better, so I just set something default. And at every time step, what I do is the following. I solve a simple least squares problem on the active set. I do that, which gives me a model. And after that, once I have this model, I try to find out which are the points that appear least corrupted according to this model. So I try to find out the points which have the least residual with respect to this model. And I use it to construct the next active set. That's it. That's the algorithm. So this is the active set. I'll call this set STB. Active set is the set of points that we believe at this moment are clean. We solve an active least squares problem on the active set, and then we update the active set to find the points which seem least corrupted with respect to the model that we have just learned. And this can be done very easily. You just find the residual vector and just sort it and just find the points with the least absolute residual values. Oh, okay, so any questions about the algorithm? Yeah, I'll come to that. This is going to be important, yes. So you get the blue curve if you take this fact into account. I'll come to this. Any questions regarding this algorithm? Are you asking for the L2 reconstruction error of the images? I don't have that. I can pull that out, but right now I don't. For the graph that I showed, the convergence graph, this where the blue curve plummeted, the L2 error was 10 to the power minus 15 or something. So it had basically found out, to numerical error, it had found out what was the clean set. Okay, so let's see how does this work. Again, this is just a toy. So this is the golden model. So I have a bunch of data points. Uncorrupted, they would have lied on this line, but my friend, who is not coming on screen for some reason, he comes and corrupts these points and just throws them out of whack. What do I do now? Well, again, I'll just do this nice alternation. So at every time step, I first take a set of points. Let's say, first of all, I take all points or whatever, and I fit a curve. Pathetic fit, doesn't matter. But the residual is very, very high. Next, what I do is I find out what are the points which look most corrupted with respect to this line. So this point would look very corrupted. These points would not look very corrupted. This point would look very corrupted, although it's a clean point. So the points that were shrunk were set aside. So these are the new. This is the new active set. I solve the least squares problem again. So something nice happened. I got closer to the model, which is exactly what I had hoped for. So again, solve the, find out for this new model, find out which are the new, what's the new active set. So very nice, something nice happened. One corrupted point got thrown out, one non-corrupted point got in, and I solved again, and you can imagine what will happen now. So within 4 iterations, I actually find out the model. And this is a real execution, so I mean, so I actually ran the thing. This is what got. So we are done. In 4 iterations, we have 0 residue. Okay. So this is what I was talking about. If you did least squares on these corrupted images, this is what you get. So it's clearly an indication that treating these corrupt as Gaussian noise or something benign does not work. But what you get using this alternating strategy is much, much better. Okay. You can actually use this for the recommendation systems problem as well. The algorithm is, I've not told what the algorithm is because this is a multi-arm bandits algorithm. It's a linear bandits problem with an explore and exploit strategy. It takes a whole other set of tools effort to get that working, but something similar happens. So this is with number of fractional corruption, but even so, the red line is what you would get. This is the regret which Swati was alluding to. What the amount of lost opportunities the algorithm experiences due to recommending items that the user does not like. So if you executed things just as before, you would get pretty high regret. But if you execute an algorithm based on this AM-RR algorithm that I just incurred, the regret that you get is much lower. And then this trend only gets more prominent as the fraction of points that are getting corrupted increases. So if you so this is 12% fraction, 12% of the points corrupted. You have a huge gap between the regret of the two algorithms. Okay, so I was about to ask all of you, or rather allow all of you to doze off because I was going to look at convergence proofs, but I'm not going to be able to do that. So just let me introduce the key concepts of why and what is required for this algorithm to work, and we'll just stop at that. Clearly, some preconditions have to be met to allow all this nice behavior to take place for this algorithm. So in particular, it had better be the case that if I had S star, using S star, I should be able to identify W star. If even this is impossible, then the whole problem is lost. So if magically someone came and gave me the clean set of points, it should be possible to use that clean set of points to uniquely identify W star, which basically means that the set of, so your high school linear algebra will tell you that this will happen if the covariates in the set S star constitute a well-conditioned linear system. what, for the purposes of this algorithm, what we'll assume is that we'll not just S star, but all sets of size n minus k constitute well-conditioned systems. Why? Because I don't know S star. So how do I even know which set to expect to be well-conditioned? And moreover, just as Ruta was alluding that in many practical cases, the presuppositions you make are usually satisfied in certain models. We'll see that in many practical cases, you actually get all such sets to be well-conditioned. And our notion of well-conditionedness would be the following, that the smallest eigenvalue of, or the smallest singular value of this matrix SS will be lower bounded. And I'll assume, again, for the sake of this talk, that this constant, the smallest singular value of this matrix is of the form alpha times n minus k. N minus k, remember, is the size of the set. So I'm assuming the singular value blows up with, the smallest singular value is blowing up with the size of the set. I've assumed that, I've already assumed that all of them. So this holds the upper bound. The largest singular value is always bounded by the size of the set. In fact, this holds for all sets, not just sets of size n minus k. But for sets of size n minus k, I'll assume that the smallest singular value is lower bounded as well. And this actually holds with high probability if the data points are sampled from a sub-Gaussian distribution. Very running out of time. So what I will do is skip the proof. So it's very simple. It's actually just 3 or 4 lines, which basically, so the key points here is that the residual that you get at every time step can be shown to be of this form. It's the corruption vector plus an error term. And this is where the positive feedback comes in. If this error term goes down, you are able to see, the residual is actually gives you a view of the error vector. So since you are taking the points with least residual, you're actually going to be, after a point, selecting only those points which have no corruption. I'll come to that. So once you crunch all by the way, this is just like MTH 101 linear algebra, nothing more than that. But if you do all that and you have to solve a quadratic equation, again, which does not take much effort, you get this, which is a very nice result. It tells you that the amount of corruption present in the active set goes down by a factor at every time step. I'm not saying the number of corrupted points go down, but the amount of corruption present in your active set will go down by a certain factor. Now, of course, I want this factor to be less than 1. And if k is less than this quantity, I'll get that. So this is where the upper bound on k comes. This is the so-called breakdown point of the algorithm. So in statistics, all robust algorithms have a certain thing called a breakdown point. Is an amount, or in this case, the number of corruptions the algorithm can tolerate before it completely breaks down, before the adversary can force the algorithm to spit out any arbitrary model as the output. So if this breakdown point is not reached, the algorithm will give you an epsilon accurate estimate in these many steps. Yes. So a better way to write this bound is in this form. So k should be less than n by 3 kappa plus 1, where kappa is the condition number of the system. Yes. So for Gaussian data, so if the data points are sampled from a standard Gaussian, this quantity is something like 60. Oh, so again, I think checking this quantity is NP hard. Should be NP hard. Why? Because we are supposed to check this for all subsets of size n minus k. Right. Of all subsets of the data matrix, that's where the hardness comes in. For the whole matrix, we didn't check. Oh, that I can say. But by the way, I think We can try that. I'll have to see. The thing is, in terms of experiments, we ran the experiments separately for the toy cases for showing the convergence rates, and all the experiments were ran separately for the biometric identification problem. So I'll have to check whether we did some modifications to suit the biometric identification problem or not. Yes. Take 15 different subsets, and if you're lucky, one of them will turn out to be S star. That's basically what this algorithm is shooting for. None of those algorithms have been analyzed. So if you're asking me for a convergence proof for those algorithms, we have not looked at. Yeah. I'll come to that. Yeah. I mean, I don't think I'll come to that, but anyway. Yeah. There are. Yeah. So the thing is, there are two things. This is an optimization error. This is something that you can bring down by running the algorithm longer. But there's an irremovable error that will come in because your data was insufficient or your data structured a certain way. No. This is purely optimization error. This has nothing to do with. In fact, this becomes more prominent when we have. We'll never do that. By the way, I think right. So in fact, the property that we require that all subsets of n size n minus k is actually a sort of a mirror image of the RIP property. If you are familiar with the compressive sensing literature, and since RIP is NP hard to test, this property should also be NP hard to test. We don't have a proof, but we think. I'll come to the adversary model. Our adversary right now is very okay. Let me just come to that. Yeah, when I come to it. I'll just gloss over this. In fact, what Shodhi was asking, you can actually work with general loss functions. You need not work with the L2 squared error, the least squares error. You can work with general loss functions as well. They need to satisfy some properties, blah, blah, blah. So again, the normalization requirement is replaced by a smoothness requirement. The well-conditioned requirement is replaced by a strong convexity requirement. But if you do, again, not going into it, there is a very natural version of that algorithm that works, again, not going into that, which will, again, giving a proof, again, the proof goes in a very similar manner, but again, depending on the strong smoothness and strong convexity properties that this new loss function satisfies, again, you get a breakdown point, which again depends on the condition number of the problem. Again, since we are almost out of time, the takeaway from this is it doesn't just hold for least squares, it holds for generalized linear regression whenever, and all the problems where your function, the loss function you're working with has nice properties. Again, I'll try to wrap up within the next 2 minutes. You can do things with kernels. Again, in case you're wondering why only linear least squares, can you do nonlinear least squares? Yes, you can do things with kernels as well. So again, not going into this. So I hope all of you are awake, because I'm just going to wrap up after giving you some open problems. So the model that we looked at was not just toy; it was actually not very useful either, because in practice, even in the most simple applications of least squares, it should at least expect some bit of dense noise. So what is there are two factors corrupting your observations, the clean observations now. One is, of course, your adversarial corruptions, which are sparse, but then you might have some noise that is appropriate to be modeled as, let's say, Gaussian noise or Poisson noise, whatever. But this noise is dense. It's present in all the points, almost all the points. Or rather, almost surely it's present in all the points. The question is, can you still now ensure consistency? So now even W star will not get zero residual error, because even the true model will get you some residual error. But can you still ensure that as you get more and more data points in the limit, you get the true model? So that's one. So these are issues. I'm not giving you solutions now. So adversary model. So you can have various levels of adversariality in this problem. You can have a fully adaptive adversary, which chooses its corruptions with the knowledge of everything else. You can have a fully oblivious adversary, which does not know anything before it is forced to give you the corruption. Then you can have partially oblivious adversaries, which know some things but don't know others. The result that I gave you, all the results that I gave you work for the fully adaptive adversary. But it may just say that if those results seem weak, it may be because stronger results are possible if your adversary is fully oblivious. We don't know. The breakdown point, very, very important point. Information theoretically speaking, you should be able to get things done with even n by 2 minus 1 corruptions. There seems to be enough signal there. What about n minus d log d corruptions if the adversary is fully oblivious? So if the adversary is allowed to corrupt n minus d log d corruption in these many points and it is fully adaptive, then you can show that there's no signal there. You can't recover the model. But if the adversary is oblivious, and this sort of goes back to Ramprasad's talk. So if you allow the adversary to look at the points before it corrupts, it can totally screw up the entire signal. So there should be no possible way of recovering the signal. But if the adversary is oblivious, there's no reason why 90% corruptions should pose any information theoretic hurdle to recovery. Again, if you are adaptive, then yes, you should not be able to. But if you're oblivious, you don't know X, you don't know W star, you don't have sign, you don't know at what scale to introduce the corruption. So in that case, you don't know the sign. Should you increase it? Should you decrease it? So again, the Reed-Muller codes were able to give those guarantees only for oblivious oblivious erasures and oblivious corruptions. So again, can you replicate that? That would be, I think, a drawback of the current state of our understanding. We don't really know what is possible if we allow fully oblivious adversaries or partially oblivious adversaries. Our bounds at the moment are mostly hold for fully adaptive adversaries. What is appropriate for that? If the malware is present on a computer, then of course it is fully adaptive because it is able to look at the current click before deciding whether to send it or not. Because if it's for an ad campaign that it doesn't care about, fine, it lets the click go. But if it's for a competitor ad campaign, it suppresses that click. Yes. Again, this is the place where the gap between theory and practice becomes a bit glaring, because the adversary model is something that should be tuned to the application, but you want an adversary model that works in theory. So anyway, I should really wrap up. Nonlinear structures and models, sometimes the linear model is not appropriate for the task at hand. What if you want to do row restriction with sparse models, with kernels, or even deep nets? Can you do that? What if your loss function is something else? We've already seen an example. Speed. The algorithm that I gave you requires you to solve multiple least squares problems. And that seems like a bit of a bored thing to do, because, I mean, why should I solve several least squares problem? Because my original problem is just one least squares problem, right? So can I invoke this least squares oracle more conservatively? And the answer is yes. I'll give you the answer in the next slide. And the other is feature corruption, of course. Again, it relates to the adversary model. What is the adversary able to corrupt? Just the responses or the features as well? Again, I'm not going to this. So we do have some answers. We are able to handle dense Gaussian noise and sparse corruptions if the adversary is fully oblivious. We don't know what happens if the... Okay. Okay, so not going into all this. Anyway, so I think I'll just stop. There's no point going over the set of So if there are any questions about, regarding the algorithm or the applications, I can take some of them. So I think I'll just wrap up by saying that this blue curve, this ultra fast curve, is one that uses the least squares oracle only if the active set has stabilized. So this relates to Nisheeth's question in the beginning. What do you do if the active set changes a lot? So if the active set is changing a lot, you don't do least squares. You just do a gradient descent or a conjugate gradient descent step. But if the active set is stabilized, you do a full least squares step. And in practice, you just do a few of them. So that leads to very simple. Yeah.
Hi. So, how would you compare your algorithm to clustering? Like, it looks very similar to like an EM or clustering algorithm. And in fact, if we project the points like in the picture that you showed, if we project it in a different space, which is, let's say, how far you are from the original model, right? It's really a clustering problem.
Yeah. So there are two answers to that question. If you look at the k-means algorithm, the k-means algorithm is an alternating algorithm. So, and this is an alternating algorithm. However, the AM algorithm is a soft version of the k-means algorithm, right? It doesn't do hard assignments; it does soft assignments. In fact, there is a soft version of this algorithm as well. But for that, you have to catch hold of Govind because he's the one working on this. So instead of just throwing away points and having an active set, what you can do is weigh points down if they have large residual and weigh them up if they have soft. So we have an EM version of the algorithm as well, and what I gave you is the k-means algorithm version. So yeah, there are parallels.